Hello, everybody. Welcome back. Today's subunit that we're going to cover is subunit 1.6, which is all about photoelectron spectroscopy, or it's abbreviated PES. And I imagine that this is a topic that will be new to most of you. So probably a good idea to have your periodic tables out, and let's get started. All right, so let me start off by saying that what is on this slide, I don't know that you all necessarily need to really focus on. Photoelectron spectroscopy is a technique where, let me get this to come up. There it is. Okay, so high energy radiation like UV, ultraviolet radiation, or X-rays are fired at a piece of an element, usually a metal, and electrons are ejected off of the surface of that metal, and the kinetic energies of those ejected electrons are measured. And there's all kinds of calculations involved in this, and I really don't want you to get caught up in the details of this. But essentially, what we're going to look at, guys, is what are called PES graphs. And we're going to learn how to read these PES graphs. And it is tied to our last lesson. It has a lot to do with periodic trends. So this is what a PES graph looks like. Okay, this is what's called a photoelectron spectrum, and this is for the element neon. Okay, now let's get our bearings here. Okay, first of all, on the x-axis, it says binding energy. That is nothing more than a fancy term that just means ionization energy. Okay, we talked about that last in unit 1.7, which I covered before this unit. It makes more sense to do it in that order for me. Ionization energy, remember, is the energy required to remove an electron. Okay, fine. The other thing I want you guys to notice is that the x-axis, if you look at the range, the numbers, it's sort of backwards from what you would think. We see the number 1000 on the left and 0 on the right. Okay, so essentially whatever's going on in peak A has a very high ionization energy, whereas whatever's going on in peaks B and C, and we'll talk about what they represent, B and C have a much, much lower ionization energy. Okay, so sometimes PES graphs will say ionization energy on the x-axis. Sometimes they'll say binding energy. It's the same thing. Okay, so this is the exact same graph. Let's talk about what these peaks are, okay? Each peak is essentially representing electrons in one particular sublevel. Okay, so what they're saying is peak A is representing, and I'll just tell you which sublevel that is. That is representing electrons in in sublevel 1s. Okay, what's in peak B are the electrons in 2s, and peak C are the electrons in 2p. All right, so what they're saying is, and this is not entirely accurate because we've talked about, ionization energy and the trends. We talked about that last time, but essentially what this is saying is the two electrons in 1s, peak A, have approximately the same ionization energy. The electrons in 2s, peak B, have a much lower ionization energy. All of the electrons in 2p, that would be peak letter C, have an even lower ionization energy, okay? So there's one peak for each sublevel. The height of the peak corresponds to the number of electrons within each sublevel. So let me just label this graph a little bit here. So this is 1s2, okay? There's 2 electrons being represented in peak A. Those are the 2 electrons in sublevel 1s. Peak B is representing the 2 electrons in 2s. I want you guys to notice that peaks A and B are the same height. They're the same height because they both have 2 electrons. Peak C represents 2p. And how many electrons are in there? There's 6. And I know it's a little bit hard to tell, but can you see that peak C is 3 times higher than peaks A and B? There's 6 electrons, not just 2. Okay. Now, again, I want you to look at that x-axis. What this is now saying, now that we've labeled these peaks, this is saying to remove the 2 electrons in 1s, right here, requires, I don't know, maybe that's like 875, okay, on the x-axis, okay, for an ionization energy. Whereas to remove the electrons from 2s is maybe 50, okay? It requires a lot less. And guys, let's review from last lesson. Why would it be more difficult to take the electrons from 1s than it would from 2s? Well, aren't the 2 electrons in 1s, aren't they much closer to the nucleus than 2s? Yes, they are. So if you look at your x-axis, I want you to almost imagine that the nucleus is over on the left side. 1s is closer to it than 2s, and let's review. Remember Coulomb's law. When the distance between 2 charged particles, when the distance between the nucleus and electrons is not that far, like between the nucleus and 1s, the force of attraction will be stronger than if it's farther away. Okay, so you always read a PES graph from left to right, and you always start with this, just like we start all electron configurations, 1s2, and you go from there. Okay, same graph again. So let's just kind of bring this together. So it says, what is the relationship between binding energy and effective nuclear charge? Well, guys, remember, binding energy just means ionization energy. As the effective nuclear charge is stronger, the ionization energy will be higher, so further to the left on that x-axis. Okay, peaks A, B, and C represent binding energies of electrons in which sublevels? Well, peak A was 1s, peak B was 2s, and peak C was 2p. Why is peak A so far to the left of B and C? Remember, peak A represents 1s. Those are electrons that are much closer to the nucleus. And according to Coulomb's law, when the distance is shorter, the force of attraction is stronger. Why is peak C 3 times the height of A and B? Because peak C has 6 electrons in it. Peaks A and B only have 2. Okay. Now, on the last PES graph, the one we were just looking at, you were told what element it was. We were told that was for the element neon, but sometimes you won't. And guys, what I would recommend, even if you are told what element it is, I still, even as a professional, I write I label my PES graphs. So this is 1s2, 2s2. This tall peak, this is 2p6. Notice it's 3 times as high. 3s2, 3p6. Okay, and then this last one, it's 4s, and is it 4s2 or is it 4s1? Look at how tall that peak is. It's not as tall as 1s and 2s and 3s. It's half the height, so it's just 4s1. So what element is this? We'll follow the configuration. 1s2, 2s2, 2p6, 3s2, 3p6. What element ends in 4s1? That would be potassium. Okay. On what energy level is the electron in the third peak? So this one. What energy level is that? Well, that's real easy when you've labeled it. What energy level is it? It's energy level 2. Okay, or they might say what sublevel is represented in the third peak, and then you'd say 2p. Okay. Oops, I guess I was supposed to let you all practice with that one. Whoopsie. Okay. Actually, let me go back. All right, what if, because I've seen a question like this, what if the question said, draw a peak that represents the valence electrons for one element or one proton greater than this element. Well, let me go back for a second. We said this element, this was for K, potassium. What element has one more proton than potassium? Well, that would be calcium, right? Okay. Let's answer the question, how many valence electrons does calcium have? It has 2, correct? And where are they? They are in 4s. Okay, well, let me just label this again. This was for potassium. And this was 4s1. Okay. If we're dealing with calcium now, okay, and it said, draw on this graph, draw a peak to represent the 2 valence electrons for calcium, watch where I'm going to draw it. I'm going to draw it right there. Okay, now let's talk about why I drew it the way I did. Number one, why did I draw it double the height to the one on the potassium graph? Well, because potassium only has 1 valence electron in 4s. Calcium has 2 electrons in 4s, so that's why I drew it double the height. Now, why did I draw it just slightly to the left of that last peak? Think about it. Calcium has 1 more proton. Doesn't that mean that calcium's valence electrons are going to experience a slightly stronger attraction for its nucleus? Yes, indeed. Okay, so the peak is drawn slightly to the left because, again, calcium's valence electrons are experiencing a stronger attraction for the nucleus, so the ionization energy should be greater, further to the left on the x-axis. Okay, let's look at this guy. One more question. I stole this from the lady on the AP Daily video. Okay, the question says, the PES data for the 1s sublevel of lithium and the 1s sublevel of sodium are represented below. A student claims that element A, the one on the top, is lithium. Do you agree with the claim? justify your answer in terms of Coulomb's law and atomic structure. So I want you to pause your video and think about it for a second. Okay. I'm hoping that you said that you disagree with the claim. Okay? We are looking at the 1s sublevel peak in both elements. Okay? Lithium versus sodium. Sodium has more protons than lithium does. Okay? So think about Coulomb's law. The magnitude of the positive charge in a sodium ion is greater than in a lithium ion. So the graph at the top, element A, that must be sodium because the peak is further to the left, meaning it's more difficult to take that 1s electron away from sodium than it is from lithium. Why? Because that electron in 1s, okay, that we're trying to take away is being held much more strongly by that sodium atom than it is by the lithium atom. Again, because sodium has more protons in its nucleus, that attraction is stronger. So sometimes you'll see questions like that. All right. So that is it for PES, okay? I wanted to do this lesson after the periodic trends lesson because I wanted to have already talked about effective nuclear charge and the trend in ionization energy before we started looking at those PES graphs. I think it makes more sense to do it after. So anyway, I hope you have learned a little something today, and I look forward to seeing you next time.